Yeah, long time. Rio from TUM to Munich. It was an interesting talk about eco-conscious design for airborne wind energy. Please, and we need to stick to the 50 years because we are already at the time.
It will be challenging. Thank you very much. As I said, maybe I should start with the title that is eco-conscious design evaluation of airborne wind energy systems for drag power kites of Companioncraft using life cycle assessments. So in the outline, I will briefly, maybe I will try to hold on a short time, but I can show you an overview first of the LCOE design tool that we have at Technical University of Munich, and then present you the technology of Companioncraft, but I guess a lot of you are maybe familiar with it already. And then our work is on the sizing model of the system and the LCA implementation, so an automated LCA implementation. And then show you some results which maybe I want to quickly focus on. So to put it into context, so what we are doing at the Wind Institute in Munich is that we want to shift into beyond LCOE. So because in the last years the cost of wind energy has been decreasing a lot. So our main research question is now that wind energy is competitive economically, how can we increase its value for the environment and for society? So for this there can be many approaches that can be taken in this very broad question. Our approach is to use life cycle assessment and to focus for now on global warming potential, which is like the CO2 emissions due to the life cycle of energy systems. So for this we define, and what you will see later on some plots, the environmental cost of energy, which is basically the global warming potential or carbon footprint in gram of CO2 equivalent per kilowatt. And one main thing is that the airborne energy systems, it has a huge potential to have a low environmental cost of energy due to the reduced material consumption compared to conventional. So briefly also, if some of you are not familiar, life cycle assessment is a non-scientific methodology to estimate the environmental impact of any service or product over its entire lifetime, so from cradle to gate. And many different environmental impact can be considered, but in this study for now we mostly focus on the climate change impact, which is expressed in gram of CO2 equivalent. And so we follow, in our approach, we follow the standards of the life cycle assessment thing. And now, so also to put the background, so this was my master thesis, which was starting to make a life cycle assessment for a conventional wind turbine. So here we can see a picture of a nice onshore wind turbine in the Bavarian Alps, and to integrate life cycle assessment in the design of conventional wind. So I can pass quickly that this was the main result. I have some of the results of this stage. So here we can see the impact in grams of CO2 per kilowatt of this conventional. And one thing we can see that the main element impact is the tower because of the massive use of steel. And we have an impact of about 15 grams CO2 per kilowatt. Then a colleague of mine has followed up his master thesis on the topic of offshore wind farm. So the same approach of having LCA but for offshore wind farm. And similarly, the results clearly showed that the main impact in this case was the turbine support structure and the tower. So this was to put the background, as it was at this point that our Professor Botasso has thought, okay, we see that clearly the tower is the main burden, environmental burden. So why don't we also try to go for airborne wind energy, because it doesn't have a tower. So probably it has much lower environmental impact. Now I can briefly introduce you the company Companioncraft, which we are collaborating with for this study. So they were founded in 2019 and they are based in Munich. Here is a recent picture. I think this year they have been expanding with some funds. So they are 4 original funders, but now they are up to 7 employees, as we can see here on the test site. And their system is a flight generation rigid drag power kite. So I just heard that maybe we should not say rigid anymore. But so here's a picture and the main elements that we want to consider in our study, of course, because we do the life cycle assessment, so we need to make an inventory of all the elements that are going to be necessary for the system. So mostly we have the kite, of course, and the airframe that we can see here on the right. Then the teller, that you're all familiar with, I guess, and the ground station, which consists of the whole foundation, and the system, the landing system, as well as the batteries and all the control system. So here, as you, I guess, are all familiar, Companioncraft is doing a figure 8 flight And I think recently they are mostly working on the control part, and they had some successful flight tests. But this was to introduce the technology. Otherwise, our focus on the study in this collaboration was to have a sizing model, so design model, and to link it with a life cycle assessment implementation. So here is an overview of the toolbox, which is also all coded in MATLAB, where we have different sub-models. So as I said, our main final goal is to estimate the cost, environmental cost of energy in CO2 per kilowatt. So for that, we have a life cycle assessment model, and it requires as input all the masses of all the components that we're going to need for the airborne system. So that is why we first start with some input parameters. Like the general idea is that we don't want to make a life cycle assessment of one fixed system, but we want it to make it dependent on design variables. So for example, we want it to be able to automatically call for a different span of the kite, or aspect ratio, or chord, or electrical power. And the model can automatically estimate the masses that would be required and estimate the impact of energy in this case. So we have these inputs that give us some normal forces, and then the sizing model estimates all the masses of the components. And one also very important part, of course, is to estimate the annual energy production of the system, which is also going to be depending on the design variables. Because in the end, the whole toolbox is made because there is a trade-off to define, just like for the cost of energy. Also for the impact of energy, there's a trade-off to be found between what the burden, so if we use more materials, but also we can expect bigger energy production. So in this whole, like having the masses and having the energy estimation, we can maybe make an optimization where we can find an optimal size of the system that has enough, that is worth to have the lowest gram of CO2 per kilowatt. So to go quickly through the different boxes. So first, as I showed we have a truss model, which take as input our main design variables, so the span, aspect ratio, chord, and installed power. And it's a model that was developed by Companioncraft internally, and that can estimate all the forces that will be needed, also to make some structural sizing, and to have the masses of the kite that will be needed for holding the forces. Then afterwards, there is a sizing model, which takes as input from output of the truss model, as well as other design variables, so mostly some inputs that can be changed with tether parameters, environmental parameters, some flexible environmental fixed variables. And in this study, we have studied three sizes of the Companioncraft kite, so which are namely the prototype KK3, which is at 5 kilowatts, then KK10, which has 100 kilowatts, and the KK20, which is at 500 kilowatts. So because as I said, we want the model to be able to estimate any kite size, but for now at this stage we have the three sizes that were estimated, and in the further step we wanted to be able to be even more flexible to take any sizes possible for the model. And here briefly for the life cycle assessment model. So we consider the global warming potential impact category. Our functional unit is to produce 1 kilowatt of electricity produced by the kite and sent to the electrical grid. We don't consider all the connections to the grid. We stop at the system boundaries of the kite and the ground station. And here we consider some assumption of 30 years lifetime, and it's located in Brandenburg in Germany. One important thing for the end of life method, we consider an open loop method, which is that at the end of life we consider the recycled materials will be used in a different application. So there's no credit given, which is in accordance to the database that we use, EcoInvent, which give us the impact by all the materials that we are using. And here on this graph are all the life stages that are considered in the model. So mostly from the raw material extraction to all the way to components manufacturing, the assembly of the kite, and then in the operational maintenance, we also have some models of the trip of the trucks that are necessary to go to maintain the system. Of course, the electricity production, which will be our benefit, and all the way to the decommissioning of the system. To jump into the results of our estimation for the system. So here first, as I said, we estimated for now for 3 systems. So here is for the first KK3 kite, that is at 5 kilowatts. We estimate global warming potential around 28 grams of CO2 per kilowatt, which is a bit high and higher than expected. But yeah, this is for now a prototype size, and as we'll see, like, yeah, I think it makes sense that for this prototype it's not yet fully optimized for power production, so this is why it has a higher impact. And here the graph, so on the left we have this impact of energy split up by components, so the kite, the tether, ground station, and some impact that are not related to any materials, and also the different curves are the materials that are in these systems. So what we can clearly see that the ground station already is a main burden in this case in terms of CO2, but also for this prototype there's a big impact of the non-material, which actually is mostly related also to the operation and maintenance, because, and I think this is mostly due to the small size of the system. So the maintenance scenario that we consider actually like relatively has a big impact compared to the energy outputs of this small system. And here on the right we have the same gram of CO2 per kilowatt, which is split by the life stages of the kite. So here in this case, as we could expect, the main impact of the raw materials extraction, we don't have, I mean, yeah, here in the OEM, it's mostly due to the maintenance. There is no direct emissions like in coal power plants, for instance. But the main two are raw materials and manufacturing that are responsible. Here to jump to the second one, so we already go to bigger size of a 100 kilowatt kite, which has a span of 10 meters, so this is a KK10. And here we already see that we go much down in the impact, so we are below, we are around 6.72 grams CO2 per kilowatt. And here in this case, we see what I was explaining, that then the operational maintenance is going down due to the fact that the same scenario of maintenance over the lifetime is much more worse due to the increased energy production because of the scaling up. So in this case, which is more maybe realistic size of a commercial kite, the main impacts are estimated to stick to be the raw material extraction and manufacturing. But still, the ground station is one of the main impacts. And then to jump to the third one, so here we have the KK20 rated at 500 kilowatts. We even go even more down, so we estimate an impact of 5.95 grams of CO2 per kilowatt for this system. And then I think overall the rest is similar. So also for the tree system, I think the conclusions are the same and coherent. Still, the ground station is the most impact. I don't know if I mentioned because of the materials. I think we can see in red, it's mostly because of the amount of concrete in the foundations. And I think also the batteries, yeah, the purple part is the batteries that we have seen also represent a significant impact in grams of CO2 per kilowatt. Now to put it into perspective, so these three systems that we've analyzed, so here on this plot, we are using the same tool that we had at TUM, the life cycle assessment tool, and we're comparing the conventional horizontal axis wind turbine with here the three Kite system of Kitecraft that I just presented. So the first one is a 3 megawatts that I had in my master thesis. Then we use the same system to have a 500 kilowatt conventional turbine in order to have a fair comparison. And the three bottom ones are the Airborne kites of Kitecraft. So here we can clearly see also the benefit of going down, upscaling, because these ones are much lower, and also the fact that yes, this like if we compare the 500 kilowatt conventional turbine and Airborne, we have much lower Airborne, which is what we had expected when we started the study, that there is a big interesting potential of Airborne wind to have a low environmental cost of energy. And also here is also colored by elements that I try to compare. So of course in blue we have the tower for the conventional, which would be the tether in terms of Airborne, and we can see that this impact completely disappears because tether is not much material consumption compared to the huge steel tower in conventional. So to conclude, and the key takeaways, we have obtained some life cycle assessment results for three different Kitecraft models, so the KK3, KK10, and KK20, which can be split into components, materials, and life stages. So this is quite interesting to understand where are the burden coming from and where can some improvements be made. In general, we are, as we expected, we observe a very low impact of energy, which is also in agreement with some other life cycle assessment studies on Airborne. And we can see that the ground station, due to the use of a lot of concrete and batteries, is the main remaining environmental impact. So maybe we need to improve our sizing model also on this part, but maybe this is also one thing that we can work on, the whole community or with Kitecraft, to maybe work on this to reduce this use of materials. And also one main output is the benefits of upscaling. So clearly we could see that if we go from a small prototype to a bigger system, we reduce a lot this drum of CO2 per kilowatt. So of course if we go bigger, we produce more energy, so it's worth it in terms of CO2 for the environment. So this was a first study, and we are now actually also having another master thesis on this work, which is mostly focusing on improving the mass sizing model, because as I said, we need this automated toolbox, and I think we have identified that if we want to be more like into doing optimization, we first need to validate and improve these mass estimations for upscaling the Kite, which is sometimes challenging because we have the prototype, but if we want to go to 1 or 2 megawatts, we need to make some work to know what will be the masses exactly. And so here is the same, here the title of my presentation was the design evaluation of Airborne Wind Energy System. And actually the next step will be not to do design evaluation, but design optimization. So actually to use this LCA to also consider it as a design merit to reduce. So here, for instance, it's done for conventional wind, that we're also doing at Munich, but we want to do it for airborne later, that we can do a multi-objective optimization to reduce the cost of energy, the monetary cost of energy, but to also try to reduce the environmental cost of energy. And then try to find trade-offs in between those. Also, what possible other work is to go on farm level for airborne. And then on the future step, what we start to do for conventional is to not only consider LCA, but also the value-based design as we go. So also maybe design the Kite based on market value and possible display CO2 emissions on the grid, electrical grid, which could also lead to different design optimal. So with this, I would like to thank you for your attention, and if you have any questions.